Okay, this is the result of the classes I had worn on Monday. So I just received them yesterday. Well, you don't really see it much, but if you remember downstairs, the table is somewhat over here, and it turns out that I always look in this region. I don't look much to the back, and I rarely look on that side. Well, I will try to improve on that. Okay, so let's start today's subject. Any questions before we start? The last thing we had discussed was electric field lines. Now, the properties of the electric field lines were, okay, they start on positive charges. And they start from positive charges and they go to negative charges. Or infinity. For example, if you have a single positive charge, let's say over here, the electric field line will start from this positive charge and they will just go up until infinity. If you have a positive charge, these are the electric field lines. Or if you have a negative charge, then these will be the electric field lines. Oh, sorry. It's the other way around. At every point, in reality, at every point there is an electric field line passing through that point, but in practice you just cannot draw any electric field lines at every point. For example, although here I am just drawing like 8 electric field lines, there is also an electric field line passing through here, another over here. From every point there is an electric field line. And at each one of those points, the electric field is tangent to the line. So for example, if you have a region of space where electric field lines have this shape, you should always put the arrows. If you look at this point, at that point the tangent line is this one. Well, since the electric field line is, in a sense, flowing in this sense, the direction of the electric field line is determined by the direction of this flow. And at every point, so from the electric field lines, you can determine the direction of the electric fields. But to determine the electric field, we need two quantities at every point. We need to know the direction of the electric field, and we also need to know the magnitude. The magnitude is determined by the tangent. And then we have the magnitude. The magnitude is determined by the density. So if, for example, in a region of space, you have the electric field lines has this shape, you know that the magnitude of the electric field line is largest in this region, where the density is much larger. The magnitude of the electric field line in this region is much smaller. Now let's specify what do we mean by the density of lines. So what is the density of lines? Okay, we mentioned it, but we have to somehow define it also. Well, let's look at a particular case. Let's say I have these electric field lines. Intuitively, we all, from the figure, when you look at the figure, you will say that, okay, the density is larger over here, it is smaller over there. But we have to be more quantitative. So your friend had said that the number of field lines per area. Okay, so let me consider such an area. So the area is large, or I can also consider this area. Well, this is the area. Or I can consider this area. So I have these lines just going in some direction. So I can just put my area like this, tilted, or I can put them like this. In both cases, the number of lines do not change, but the area changes. So can we be more specific than saying number of field lines passing through an area? So this was the proposal of your friend. Is equal to the number of lines divided by area. Now this is correct, but missing just one ingredient. You see, because as I said, you can put your area like this. If the electric field lines are moving in this direction, let's say in this point, you can put your area like this. Then the area through which these three lines pass will be small. Or you can put the area like this. In this case, these three lines will pass an area from here to there. So it will be a large area. So this is not a good enough definition. We shouldn't have that arbitrarily. The density should be uniquely defined. Well, related to that, let's say perpendicular area. Or in a sense, the minimum area through which those electric field lines pass, they will be the same. So the idea is you pick up an area such that it is perpendicular to the electric field lines, and then count the number of field lines passing through that area, and then divide that number by the area. That would be uniquely define the density of lines. Well, let us revert that. Number of lines will be equal to density of lines multiplied by the perpendicular area. So if we know the density, we can determine the total number of lines. Or one thing I forgot to mention, when you are drawing magnetic field, electric field lines, you have to first fix your convention. You can decide, it's arbitrary, up to you, it's mainly for practical reasons, that per 1 coulomb charge, you will draw, I don't know, 10 electric field lines. If you fix that convention, and if there's a 2 coulomb charge somewhere else, from that charge you have to start a 20 electric field lines. You have to be consistent, but as long as you are consistent, it doesn't really matter how much field lines you will draw. So the number of lines is the density of lines times the perpendicular area. Okay, that's great. But you know, the density of lines gives me the magnitude. Well, the density is proportional to the magnitude of the electric field lines. That is how we define them. So if in a region of space the electric field lines are denser, in that region the electric field is stronger. If they are less dense in a different region, then in that region the electric field is weaker. So we have this quantity, electric field times the perpendicular area. And well, in a sense, you can say that this will be proportional to the number of lines. And this is defined as the electric flux. Well, let's try to put this expression into a more mathematical, more concrete form. Let's say just for simplicity, let's assume a region of space where we have the electric field lines are uniformly spaced. In this case, the definition of the perpendicular area is kind of straightforward. They are all parallel, so if you just consider this plane, it will be perpendicular to the electric field lines everywhere. This is our perpendicular area. Now let us consider some other area, not necessarily perpendicular. Let me consider this area. Well, that area is not perpendicular. So to calculate the flux, I shouldn't multiply the electric field by this total area. Let me call this area the perpendicular area A perp. This is the red area is some other arbitrary area. Now, I will just consider a very simple case. Just imagine this book. The electric is a rectangle. What's the area of the rectangle? Multiply the sides. Now let's imagine we have some electric field lines in that direction, but I put my book in this form. So the perpendicular area should be the rectangle over here. Well, that area can be obtained by multiplying this side by this height. But this height is nothing but the length of this side multiplied by the cosine of this angle. So if I define this angle over here to be, let's say, theta, then this perpendicular area is nothing but A times cosine theta. Then the flux becomes the magnitude of the electric field in this point multiplied by some arbitrary area multiplied by cosine of the angle that the area makes with the electric field lines. So if the angle between this area and the electric field line is defined in this way, then I just multiply with the cosine of that angle. Okay, the original definition of the electric field used the perpendicular area, but instead of choosing a specific area, which is supposed to be perpendicular, now I can choose an arbitrary area that I like. The only thing I have to keep in mind is I have to multiply it with cosine theta. And theta is defined over here. You have the electric field lines. Well, you imagine the perpendicular line to the electric field lines, and theta is the angle between this plane and this perpendicular angle. Does this remind you of anything? You have some magnitude of some vector multiplied by cosine theta. Right? It looks like dot product. And in fact, we do define it as the dot product. Now, of course, we have to identify this area vector. A is called the area vector. Now, from the definition, the magnitude of the area vector should be A, should be the area itself. Now, what about the direction? You see, I want the theta angle to be the angle between this area vector and the electric field. Now, at this point, the electric field is in this direction. So whichever area vector I define, it has to make an angle theta with this. But you see, this angle over here is 90 minus theta. So if I draw a perpendicular line to my area, if I consider this vector, this angle over here is also theta. So this is how I define the area vector. So I have an area, given an area, I can define a corresponding vector. The magnitude of this vector is the area I have, and the direction of that vector is perpendicular to my area. And now I have the area vector, so the flux just becomes the scalar product of two vectors. Again, just keep in mind that this is, in a sense, just the number of field lines that is passing through your area. Questions? No, not always. This is just a special case. But then what do we do in the other cases when the electric field lines are not so parallel? Well, the only constraint I have is they cannot cross each other. Because you see, at every point, the electric field has a unique direction. So the line passing through that point has to be tangent. So they cannot cross. If you have two lines crossing, for each line, you have a different tangent line. So by definition, they cannot cross. Now the next question, not all electric field lines are, as your friend pointed out, they are not parallel to each other. So then what? But in that case, we do the usual trick that we always do in physics. Divide into small parts. You see, whatever you have, let us just imagine such an electric region of space with such an electric field lines. They do not cross, but definitely they are not parallel to each other. They make various angles. But you see, if you look at close by, just look at this region. Just look at this very small region. Enlarge it. Probably still they will not be parallel. But take an even smaller region and enlarge it. Now they will be parallel. Well, these are parallel. So if you take a sufficiently small region of any curve, in fact, it will be a straight line. And for the electric field lines, you have many curves that do not intersect, that go nearby, but they don't intersect. If you look at sufficiently small regions of them, they will be parallel to each other. So that is basically the trick. If you have an arbitrary region of space, you see, here we have many electric field lines. The electric field is not uniform. If I want to calculate the flux, what I do is flux passing through some area. Let's pick this area. What I do is I divide that area into very small bits. Within each one of these very small areas, the electric field lines are parallel. But if the electric field lines are parallel within that very small region, I can use this expression. But the A will be a very small area. So the flux passing through this whole curve, or if you just pick up one of that segments, will be just E dot dA. Again, I imagine this area divided into very small bits. For near each one of those very small bits, the electric field lines will be parallel. So I know how to calculate this quantity. If I can calculate this quantity for a very small region, again I repeat, this is in a sense the number of field lines passing through that very small area. The total flux will be the total number of field lines passing through that area. So I just sum up the lines passing through each one of those areas, so I get the sum. And that sum of over very small quantities just becomes the integral. This is the flux or electric flux passing through an area A. You are integrating over whatever area you have. I'm not assuming it to be a constant. You see, how do I calculate that? I take this very small area. Since that area is very small, over that area, E is constant. Since it's very small, in that area it doesn't change. So E is constant in that area. I multiply it with the area vector over there. Then I go to the next segment. The electric field in this very small area, within this area is constant, but might be different from this area. So depending on if I'm calculating the flux passing through this very small area, I have to put here the electric field passing through that area. If you like, we can put it explicitly over here. This is the electric field passing through the point RA. The electric field is not small. You see, the electric field over here is not small. It can be large. What is small is the area is small. So that's why E doesn't have a D. It's whatever the electric field over there. But dA is the very small area that I defined over here. Well, if you like, you can say d phi. This is the contribution to the flux from that very small area to be E dot dA. And this flux is essentially proportional to, let's say, the number of field lines passing through your area. Other questions?
It's not uniform.
Need not be uniform. Yes, because you see, the previous expression, we argued for this expression assuming that the electric field was uniform. But now in this region, the electric field is no longer uniform. One problem, the angle is constantly changing, the magnitude is constantly changing, so we cannot just take the if you want to apply that formula, okay, you have an idea about what the area is, area of the surface is known, but which electric field will you put? The electric field over here or the electric field over here, they will be different. So we cannot apply that expression in a straightforward manner. But what we do is we divide the area into these small bits. Since they are so small, within that very small area, the electric field does not change. Since the electric field does not change, I know which value of the electric field to put in my above expression. It's uniform over my area. I multiply it with my area vector at that point, by the way. So you see, since I divided this region into very small bits, for each one of these bits, I have a dA vector. It also changes from point to point. You see, this area, this very small area is positioned like this. So the area vector over here is pointing in this direction. Whereas the area vector over here is pointing in this direction. The area is inclined like this, so the area vector will be pointing in that direction. So this is the area vector in each segment. This is the electric field in that segment. And I am summing these products for each one of the segments. That gives me the total flux. Well, there's one question you didn't ask. Okay, so if this is an area, a flat area, I said that the area vector is perpendicular to it, but there are two perpendicular directions. Which one to choose? You see, this vector is perpendicular to my area, but this vector is also perpendicular to my area. I basically have a choice over there. Well, okay, so let's draw the electric field lines. Let us assume the electric field line is moving like this. So you are proposing to choose it like this. That's a choice. But the other one is also good enough. It's also as good. You see, when you have this surface, we also would like to distinguish between electric field lines going in this direction and electric field lines going in the opposite, crossing this area in the opposite direction. We will also distinguish them. And to distinguish them, what we will do is, remember, the flux is the number of lines. Well, if the flux line, the electric line is passing the area in one direction, we will call that +1. We will count it as +1. If it is passing in the opposite direction, we will call it the -1. So when we are counting, so if you have such an area, and the electric field lines are doing like this, and if we count this one as +1, this one will be -1. So the total number of electric field lines passing through that area will be 0. Now, which one to count as plus, which one to count as minus, up to you. You can choose, as long as you are consistent. Another thing will be, suppose you have such a surface. This time it is closed. So let's say this is the region 1. This is the region 2. What is inside of that surface? I have two regions. Region 1 or region 2 is the inside. Which one is inside, which one is outside? Why? Well, you are essentially saying that one is finite, the other one is infinite. Forget about the size. But is there anything that distinguishes those two? Now you see, for example, I don't know if there is another surface, let's say, right over there. Or I don't know if the universe ends over there. I don't show it over there. You see, even the definition of inside and outside has some kind of arbitrariness. Okay, intuitively we know, I'm sure all of you will define region 1 as inside, but mathematically speaking, there is no reason to define region 1 as the inside and region 2 as the outside. You can as well define region 2 as your inside and region 1 will be your outside. Now this will be important because the area vector for this surface, for this closed surface, will be pointing from inside to outside. So if region 1 is inside, then the area vector for that surface, let's say at this point, will be pointing in this direction. The area vector at this point will be pointing in this direction. It will be perpendicular to my surface, and also it will be pointing from inside to outside. So it's just the choice, or the definition, let's say. Just like which direction should we choose the area vector? Up to you. You can choose whichever one you like. But once you choose the direction of that area vector, that vector points from inside to outside, always. So I could have chosen the area vector to be pointing like in the opposite direction. In that case, I would be defining the outside as the inside, and this one will be the outside. Again, it's just a definition. Doesn't really have a deeper mathematical meaning. Okay, so back to flux. So we now know how to calculate the area vector, how to define the area vector, the electric field we had discussed. Any questions on how we define this flux? We will make applications on that. But once we establish the concepts, then we will do some examples. Questions? Now, let me take a point charge, an arbitrary one, and let us fix our convention. For a charge Q, I will draw 8 electric field lines. Agreed? Do you agree? And let me also consider another case. I have a plus Q over here, I have a plus Q over here, a minus Q over here. So here I will draw 8 electric field lines. Since it's a positive point charge, the electric field lines will be just radially out. How many of them are there? We had fixed the convention. 8 of them. Now let's go to the other case which we have the dipole. We had discussed the electric dipole and the electric field lines of the dipole. Well, there will be one that goes straight from the positive to the negative charge. Well, there will be those others bends. There will be this one going straight out. Again, I stick with my convention. For each plus Q charge, for each Q charge, there are 8 electric field lines. So this is a plus Q charge, so there are 8 electric field lines leaving that charge. Here, this is a minus Q charge, so there are 8 electric field lines entering that point charge. So now let me count the number of electric field lines passing through this area. So how many electric field lines cross that area? Imagine there's just a closed area, not just a line. Well, there are 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Or flux is 8. Let me imagine another area. What is the flux of that area? It's again 8. I changed the area completely. I shifted it. I deformed its shape. Nevertheless, the flux is still 8. Let me choose a different area. What is the flux? Do you see this line? Okay, what's the flux? I will say 0. You see, any line that passes from inside to outside counts as 1. Well, that is the convention I chose. And any line that goes from outside to inside counts as -1. So let's see. Here there is a line. It goes from outside to inside. It crosses my surface once, but from outside to inside, so that is -1. But here the line crosses my area from inside to outside, that's a +1. So if I add them, they just add up to 0. You see here, the area vector is pointing in that direction, in the opposite direction as my electric field. So the scalar product will be a negative number. Here, this is the direction of the area vector, it is the direction of the electric field. So when I take the scalar product, it will be positive. If I add a negative number with a positive number, it's just 0. Similarly here, this line crosses from outside to inside, -1, and then from inside to outside as +1. When I add them up, it gives me 0. You see, let's go back to the red surface. There is this line passing from inside to outside, +1. There is this line passing from inside to outside, +1. This line also from inside to out 1, +1. All the lines crossing the surface goes from inside to outside because inside there is my charge, where there is the source of electric field lines. So any electric field line created by this source crosses my surface, but in this case, for this surface, it crosses my surface once. But in this case, inside my surface, there are no sources. Whatever electric field line enters my surface, it also enters the interior, it also leaves the interior. So the sum is 0. None of them terminates inside, and none of them start inside. So that is why, for this area, the flux is 0. It's not that the electric field is 0, but there are both positive contributions to the flux and also negative contributions to the flux. They add up to give 0. Well, let's look at the other case. For this area, what is the flux? Well, let's see. How many, from this plus Q charge, there are 1, 2, 3, 4, 5, 6, 7, 8 lines starting from the plus Q charge. All of them start from the inside and go outside, so all of them contribute 1. So the flux is 8. Well, it is just like this one. You see, although there is this minus Q charge on the other side, it didn't change the flux. The only thing that minus Q charge did to the field line leaving plus Q charge is it just bent it. Instead of starting from here and going radially outward, those electric field lines started from there and bent toward the minus Q charge, but it just didn't change the number. The number is still 8. That one, no, that's also leaving out. So any charges outside didn't change the flux passing through it. It just bent the electric field line, so it bent its direction, but the number of field lines is still the same. Now, if I would imagine, let's say, an area around the minus Q charge, the flux is minus 8, because there are 8 lines passing through my area, and all of them are going from outside to inside. Let me imagine one more. What about that closed area? Are you convinced that it is 0? Those on the back? You see, if you remember the definition of the flux, if electric field is pointing towards the area vector, then the flux is positive, because the scalar product will be positive. If the electric field is opposite to the area vector, then this flux will be negative, because the scalar product of two vectors whose angle between them is larger than 90, it will be negative. So if you look at this area, on one hand we have this point, this is the dA vector at that point, and then we have this point. You see, we have this point. At this point, this is my area vector. The electric field vector is pointing in this direction. So this is the area vector. This is the electric field vector. The angle between the two is less than 90 degrees. So cosine of 90 is a positive number. So the contribution of this crossing is positive, and in fact plus 1. The contribution from this crossing of the surface is the electric field vector is in that direction. This is the electric field vector. The area vector is in that direction. The angle between the two is larger than 90. So the scalar product is a negative number. So the contribution from this crossing is minus 1. When I sum the contribution of this line only to the flux, it is just 0. Well, all the field lines that enter my surface also leave the surface because there are no charges inside. If there were some negative charges inside, some of these electric field lines would have terminated on the negative charges. So there will be a negative contribution, but there won't be a corresponding positive contribution. If I had positive charges inside, some electric field lines would start from that positive charge, and they would just cross the surface from inside to outside, so they will contribute positively. So the number of field lines passing through the surface, whatever your surface is, always proportional to the charge. So E dot ds, let me put this sign, E dot dA. So this is an integral over a closed surface. This E dot dA integral always has to be proportional to charge enclosed, charge inside the area. So how do you define the inside? Well, it is the opposite direction of dA. So the choice you make for dA defines what you mean by the inside. And also this integral would be independent of the surface area. Whatever surface area you choose, as long as the charge inside the area is fixed, the value will be the same. And if there are charges outside that closed surface, you see, as in this case of the electric dipole, you see the existence of that minus Q charge outside changes the electric field on that red surface. So this electric field changes if there are charges outside your surface. But nevertheless, the value of the integral is independent of the charges you put outside your surface. For example, for that blue surface, if you don't have any charges, let's imagine plus Q charge and minus Q charge, they are absent. E dot dA integral is 0. And because the electric field is 0 everywhere. If I put a plus Q charge over here, just a plus Q charge, still E dot dA integral will be 0, but the electric field will not be 0. We will have a non-zero electric field. Nevertheless, this integral, the value of this integral will not change. Or if I put a minus Q charge over here, still, although the electric field changes, the value of this integral does not change. Any questions before you go for a break? Yes.
Şimdi flux sıfır oluyor ama numarası sıfır olmuyor yani.
Now the number of field, you see, for this blue surface, there are crossings, there are field lines that cross the surface, but they cross it twice. Once they go inside, once they go outside. As they go inside, their contribution is minus. As they are going outside, their contribution is plus. They add up to give 0. The sum is 0. Although there is this electric field line passing through my surface, its contribution to the flux is 0. Okay, let's give a 10-minute break.